Hello there, Prof here. Welcome to Tech Foundation. Previously on Electronics 101, we talked about electricity, why electricity is preferred to other forms of energy, the origin of electricity, electrostatics, and current. In this episode, we will be talking about electrical resistivity and conductivity, electrical potential energy, and electrical potential. Let's get started. In electronics, we design circuits with various materials and components. Every material has an intrinsic property that quantifies how strongly it opposes the flow of current. Usually, people get confused about resistivity and resistance. Before I get to an in-depth explanation, I want you to note that resistivity is not the same as resistance. A material with a low resistivity means that it offers little resistance to the flow of electric current. Resistivity is represented by the Greek letter rho, and its SI unit is ohm meter. So that is rho, and its SI unit is ohm meter. Resistivity is an intrinsic property of a material. Now, what this means is that if I take different sizes, length, weight of the same material, the resistivity value would be the same. Therefore, any piece of that material, so let's say if we take copper, irrespective of its shape, size, or weight, the resistivity still remains the same. The inverse of resistivity is conductivity, which is a measure of a material's ability to allow the transport of electric current. Conductivity is measured in Siemens per meter. Okay, so let's look at electric potential. Let's say that we have an empty space and we put a positive charge at the center. From Coulomb's law, this positive charge will be exerting electric force all around it. Okay. Now, the electric force it exerts, according to Coulomb's law, is stronger the more you go closer to it, and weaker the more you move away from it. So when we put another positive charge in this space, so let's say we put one here, one there, and another one here, these charges would experience the force exerted by the positive charge. Now, the magnitude of the force that each charge will experience will depend on the distance between its center and the center of the positive charge, meaning that the influence of the force exerted by the positive charge will be different for all these charges. So F1 will be different from F2 and will be different from F3 because the distance of separation are not the same. The region of space around this charge, this positive charge, where its electric force can be experienced by the test charges, is called the electric field. Now, electric field is therefore, by definition, electric force per unit charge. Electric field in itself is a vector quantity. That is to say that it has both magnitude and direction. From basic mechanics, work is said to be done when a force moves a load through a distance in the direction of the force. Therefore, the force exerted by this positive charge is capable of doing work on any test charge that is put into its vicinity. So, if I mount another test charge here, which also happens to be positive, then it can be repelled by this positive charge to move a distance r. This will mean that work has been done on this test charge by the force of the positive charge. So, the force exerted by the positive charge has the capacity to do work. This capacity to do work is what we call potential energy, and it is as a result of the position or configuration of the electric charges. Okay, so In this same field, the potential energy on F1 will be different from that and that and that because of their configuration or positions in this electric field. So we can consider the area around this positive charge here as some sort of potential energy field. The potential energy is, however, dependent on the charge that will be brought in the vicinity. For instance, if these charges have different values, let's say this one is 1 coulomb, 2 coulomb, and 3 coulombs, then their potential energies are also going to be different, because the electric potential energy, as we see here, U, as we have defined here, is dependent on both the positive charge and the test charge. How about we try to write the potential energy field in terms of numbers, okay, with each number representing the magnitude of the potential energy at that point. To do this, we will need to assume a unit charge for all points around the positive charge. Okay, so what we are doing is we are inserting point charges. So let's say that each spot here, we fill it with a unit charge. Okay, so that at the end, this Q becomes the same for all of them. Is that okay? Then we would define a quantity V, which would be expressed as the potential energy U per unit charge. Is that okay? So the potential energy at every point per the charge of the test charge that has been placed there. And you know that results in a new formula. We get this new expression, K times Q over R. And this K times Q over R is what we call voltage or electric potential. So electric potential is a scalar quantity. So electric potential is a scalar quantity that shows how much work will be done on a unit charge at a particular point in space and in an electric field. It has units of joules per coulomb, or we also like to call it volt. Now, because we can choose the zero of the potential to be any point in the given space, voltage alone is not physically meaningful. However, difference in voltage between 2 points is a meaningful quantity. So when we take 2 points and find the voltage difference between them, and we have what we call the potential difference. So whenever we talk about voltage, we should rather consider it between 2 points. In electronics, voltages are usually measured with respect to ground, which is the point of convergence for all currents, and it's usually taken as the 0 volt. Alright, so that is a few things you need to know about electric potential without getting confused about all the physics in there. Okay, so let's talk about electrical resistance. Resistance is the opposition to the flow of current. The higher the resistance of a wire or a component, the lower the amount of current that would be allowed to flow through it. Now, because electronics is mostly about controlling the flow of electrons, sometimes we deliberately insert materials with known resistances in circuits to oppose the flow of current, so that a calculated amount of current will be allowed to pass through the circuit. These circuit elements are called resistors, and we shall talk about them later. The inverse of resistance is conductance, which is measured in Siemens. Every material has some amount of resistance except superconductors, which are theoretically having zero resistance. The instrument used to measure resistance is called the ohmmeter. Okay, so this is a very funny analogy explaining voltage, current, and resistance. Okay, so this man here is representing resistance, and you can see that he is trying to squeeze or block this passage, but voltage which is the force or the energy acting on the electrons, is also pushing the current, which in this case are the electrons, through the space, or through the wire. Okay, so anytime you really want to understand the difference between voltage, resistance, and current, I think this particular image is a very good one. Okay, so let's also look at electric power. Power is defined as the rate of doing work. Therefore, in electric circuit, we can define power as the rate of energy consumption, because work done is a form of energy. Okay, work is measured in joules, energy is measured in joules. Okay, now power is measured in watt, that is joule per second. Now, please note, usually you hear people talking about batteries storing power. Please, batteries do not store power. Batteries store energy. Batteries store electric energy. Okay, so this chart here, we call it the power wheel, is showing the various relation between power, voltage, resistance, and current. So with this chart, you can perform a lot of calculations whenever you have any of these parameters. So if you are given let's say current and voltage, for instance, you can calculate for power using this relation. If you know voltage and resistance, then you can calculate for power using this relation. If you know current and resistance, you can calculate for power using this relation, and so on and so forth. Okay, so I hope this helps. Don't forget to subscribe and like our videos. See you in the next episode. I am Prof, and this is Tech Foundation.